Let us continue with the description of our processor, using for that the two examples of the first lesson. The first example was a temperature controller executing this algorithm. Observe that the algorithm has been slightly simplified. We have assumed that the temperature accuracy is equal to 1 degree instead of half a degree. Thus, if the measured temperature is smaller than the desired temperature defined by the position of a mechanical selector, then the output is equal to on. If the measured temperature is greater than the selected temperature, then the output is equal to off. And if the measured temperature is equal to the selected one, then the output value doesn't change. To implement this algorithm, we will use our generic system. The measured temperature is read from input port 0. The selector position read from input port 1. The off output is available at output port 0. And an additional external component, namely some kind of clock, is necessary in order to execute this instruction. So we will assume there is an external clock connected to input port 2 that generates the current time, the value of the current value of the time. We assume that our processor is able to execute this set of instructions. To write a value within a memory element, a constant value A, to transfer to a memory element the value of input port number J, to transfer to output port I the value of an internal memory element xj, to transfer to output port I a constant value A, to compute the sum of two memory elements and store the result within a memory element, the same with the subtraction. Then to jump to instruction number n, to jump to instruction number n if the contents of memory element I is negative, and the same if memory element I has a positive value or stores a positive value. Other characteristics, for example, the number of bits of the ports and of the variables of the memory elements, or the total number of ports, will be defined later. In order to execute the temperature control algorithm, some internal memory elements are necessary to store algorithm variables. We have chosen to use x0 to store the value of the measured temperature. It is read from input port 0. We will use x1 to store the select the position read from input port number 1. X2 will read the time from the external clock. X3 will also read the time. It will be the initial time of our wait instruction. Then we will use X4 to store computation results. And finally, X5 to store the constant value 10. As regards the operations, we only need 2, addition and subtraction. The latest is implicitly used to compute conditions such as xi positive or xi negative. Let us start the generation of the program, and first under the form of a flow diagram. First instruction is the storing of constant value 10 in memory element x5. After that, we read the value of the measured temperature and store the value in x0. After that, the same with the selector position, we store this value in x1. Then we compute the difference x0 minus x1. That is to say, the difference between the measured temperature and the selector position. If this difference is negative, that means that the measured temperature is smaller than the selector position. Thus, the on-off output must be equal to on or to 1. Then we, in the case that x4 is not smaller than 0 and that x4 is greater than 0, that means that the temperature, the measured temperature, is greater than the position. Then the on-off output must be equal to off or to 0. Finally, in the third case, that is when both temperature, the measured temperature and the position of the selector are equal, then the value of the output port on-off doesn't change. Now it remains to execute the instruction wait for 10 seconds. For that, we read the time from the external clock the first time. Then it will be the initial value of this part of our program. Then we read again the value of the time. We compute the difference between both times. This is the elapsed time from the beginning of the execution of this instruction. After that, we compare this value with the constant value 10 stored in memory element x5. If the difference is negative, it means that the elapsed time is smaller than 10, so we continue reading the value of the time. On the contrary case, if the elapsed time is equal to 10, then we go back to the beginning of the program. Then, to get the program under the form of a sequence of instruction, it is just a matter of assigning numbers to the instructions. For example, the first instruction is number 0, then 1, 2, 3, 4. Here there is a jump. If the condition doesn't hold, we go to 5. Once again, if the condition doesn't hold, we go to 6. 6 is a go-to instruction, go to 10, as you can see. We assign number 7 to this instruction. Then from 7 we must jump to instruction number 10. For that we use instruction number 8, go to 10. After that we have, here we had instruction number 9, so that the conditional jump 4 is the instruction if x4 is smaller than 0, negative, then go to 7. In the contrary case, we go to 5. Instruction number 5 will be if x4 is positive, number 5, then go to 9, and in the contrary case, go to 6, and 6 is go to 10. After that we have 11, 12, 13, 14. 14 we jump to 11. And from 14 we go to a jump, instruction number 15, to instruction number 1. The second example is a chronometer defined by the following algorithm. We will assume that our system generates the output time under the form of a number of tenths of seconds, and that another circuit will transform this information to a number of hours, of minutes, of seconds, and of tenths of seconds. Then we will connect switch reset to input port 0, switch start to input port 1, switch stop to input port 2, and the reference periodic signal to input port 3. As regards the output, it will be connected to output port 0. In this case, we will use 4 memory elements. X0 will store either reset, start, stop, reference signal, or some computation result. Reset, start, stop, and ref are read from input port 0, 1, 2, and 3, and the computation result is internally generated. X1 is used to store the initial value of the reference signal, initial value within a loop. X2 store the value of time, the internally stored value of time, and X3 stores constant 1. As before, we first generate the program under the form of a flow diagram. First, we store 1, the constant value 1 in X3. We read the value of reset. If reset is equal to 1, so X0 is positive, then we put X2, the value of the time measured by the chronometer, equal to 0, and we transmit this value to the output port, and we go back to this instruction. If reset is equal to 0, then we read the start value. If start is equal to 1, then we read the value of stop. If stop is not equal to 1, in other words, if it's equal to 0, then we continue. First, we read the reference signal, we read it another time, we compute the difference with the two readings of the reference signal. If this difference is positive, it means that the first value was 0 and the second value was 1, so that we have just detected a positive edge of the signal, on the reference signal. In this case, when this difference is positive, we must update the time, adding the constant value 1 to the current value of the time, and transmit this value to the output port. And we go back to this instruction. In the other case, if the start signal was not equal to 1, then we had to go back to the beginning of the program, and the same if the stop signal is detected equal to 1. The detection of the positive edge on the reference signal works correctly if the instruction execution time is much smaller than the reference signal period, that is to say, smaller than 1/10 of a second. Now, as an exercise, try to generate the program that corresponds to the previous diagram. For that, you must assign number to the instructions. In the case of instructions like this one, you assume that this instruction has been given number I, so the next one will have number I plus 1, and the piece of program, the corresponding piece of program, is this one. In the case of a jump, if the jump is instruction number I, then if the condition doesn't hold, you must be to instruction number I plus 1. If the condition holds true, then we go to some instruction number J, and the corresponding piece of program is this one. Finally, sometimes we will have to add some jump instruction, like this one, instruction number I, go to J with this corresponding piece of program. This is a possible solution, and you can check that the instruction number assignment is correct. So this is the resulting program. Summary of this week as regard the design of a simple processor. A generic system called processor has been partially defined. It allows implementing many different algorithms, and two simple examples have been described.